Heureusement, mon français est très mal. Je crois qu'il n'y a pas beaucoup de gens qui comprennent russe. La salle. C'est pourquoi je parlerai anglais. I will speak English because that's the language which I can express myself and will be understood by everybody. First of all, let me tell that I am very grateful to Union d'Assurance de Paris for this extremely honorable prize. And I think that the fact that it was given to me this time somehow reflects the attitude to Soviet science in general and to Soviet mathematics and theoretical physics in particular. As a mathematical physicist, I decided to take a subject for my address which will not be too technical, taking into account the interests of the audience. So I will speak on very general considerations about the connections between physics and mathematics with the perspective of some speculative comments about possible future state of theoretical physics. It's quite you can hear quite a lot in recent times that people are puzzled why mathematics is so effective for theoretical physics. Eugen Wigner even coined the term unreasonable effectiveness in his paper. And in fact, there is reason for discussing this, because physics is a natural science and mathematics is play of human brain. And it's not completely clear that human brain must be somehow work in such a direction that its inventions will have meaning in natural science. Nevertheless, it's true, and so I will not be able to, I will not discuss the problem how to understand it. Instead of this, I will take it for granted and try to tell you what can you say if you believe that this is so. Before doing it, still, maybe I will give you a couple of very classical examples of these exotic and non-trivial connections between physics and mathematics. Let's take geometry. Geometry comes out of human practice, and in classical times, it was axiomatized, let's say, by Euclid, and you remember from your school about 5 Euclidean postulates of geometry. And one of them, number 5, people did not like and tried a lot to somehow to get rid of it. And only in the beginning of previous century, due to work of geometers, Lobachevsky in particular, it was understood that this postulate is independent of others, and really this development have led to invention of new geometries, Riemann geometry in particular. So this was first abstraction from practice, then internal development of mathematics, which led to a completely abstract mathematical notion of Riemann space. And now, in this century, Riemann spaces become to be a major part of theory of gravity of Einstein. And so it returned back, the notion which somehow developed inside of mathematics, returned back to physics and become extremely fundamental in formulation of our understanding of nature in this century. The same with algebra. Algebra, once more, appeared as a tool to solve, to calculate, to solve some particular problems. Then people begin to ask a question about possibility of solving of all algebraic equations in terms of radicals. And in the Middle Ages, it was always people believe that in the end they will find it. You know these beautiful stories about Tartaglia and other people, Italian school, but at the beginning of previous century, once more, Galois have shown that in fact this conjecture is not true. And the development of Galois have led to the creation of the notion of group theory, which through Sophus Lee become a theory of continuous groups. Once more, completely abstract mathematical notion which developed inside of mathematics, inside of its internal development. And now, theory of Lie groups is a cornerstone of symmetry, of describing symmetry in physics, and also one of the most fundamental notions of theoretical physics. So this is really amazing historical examples which shows this effectiveness of mathematics and physics, and unreasonable, I don't know, Wigner says unreasonable, maybe reasonable, maybe not. We don't know why it is so. So let's take this for granted, and let's try to go further and from our knowledge at this time to maybe to make some speculative predictions. To do this, I must tell you a little bit about what we call the main structures of theoretical physics, because we are still to formalize something. I will not write any formulas. I will say them in words, but at least I hope that you will have some feelings what I have in mind. In the modern description of theoretical physics, we have two main notions. One of them is observables, another is states. So observables are anything you can imagine or which exists in a description of given physical system. So in mechanics, these are coordinates, momenta, angular momenta, energy, and so on. In the field theory, you can add field variables, field strengths, and so on and so forth. The set of observables is infinite. There are many of them, and as I say, it's the main object which, in terms of which you begin axiomatization of modern physics. Now, what are the structure? What can you do with observables? Before saying this, let me tell you about states. Observables in this sense are kind of abstract notions, and we know about them making observations. And observations produce what we call states. I think that one of the best definitions of a state is the following, that state is a probability distribution, is an assignment of probability distribution to any observable. So given a state, you have a probability distribution for any observable in your set. We suppose that number of these states is big enough. So for instance, it divides set of observables, which means that if two observables have the same mean value in one state, then they coincide. In all states, excuse me, then observables coincide. If you take this axiom, let's say, as true, then it immediately follows that set of observables is a real linear space. You can add observables. You can say what is the given two observables, what is their sum, or you can multiply them by real numbers. And also, which is more important, which is as important as this linear structure, is that you have a notion of a function of any observable. Given an observable and function of one variable, you know another observable, which is a function of given one. For any real function and given observable, you can construct a new one, which will be called function of this observable. That's all about statics in description of physical system, and dynamics is introduced by another structure, which is less evident, but nevertheless is quite common in our applications, namely the Lie bracket which you are to introduce in set of observables. So when this thing is introduced, you say that the algebra of observables, now we use this term, is a Lie algebra in particular. And of course, the notion of Lie bracket must be somehow consistent with the notion of function. All these things you can write down explicitly. So anyhow, you can forget my particular words, but what is important for the following is that the set of observables is a well-defined mathematical set with some particular structures. We could formulate those structures in previous century. Hamilton or Sophus Lie was able to do it, but somehow they were not prompted to it much, strongly enough. And this more modern way of describing of this axiomatization, which I refer to, appeared mostly after formulation of quantum mechanics. But nevertheless, it applies to classical mechanics as well. And this is important for what I will say in the moment. But before, I will tell that I have learned these attitudes mostly from my American colleagues, Professors Irving Siegel and George Mackey. Mackey has a special book about foundations of quantum mechanics, and you can find quite refined axiomatization of quantum mechanics in his book. But of course, if you read it properly, then you see that the same axioms applies to classical mechanics. And so classical mechanics and quantum mechanics are just two different realizations of the same general structure. Now we turn to pure algebra, and I will just refer you to the notion, and one more notion in pure algebra, which is notion of deformation. If you have a set with some structures, and which allows for different realizations, so to say, especially if your realization, so all formulas, sum, product, notion of function, Lie bracket, and so on, can be written as a formal series containing a parameter. You are speaking about deformations. And parameter which come into your formula is parameter of deformation. Given structure, and you can try to formulate theory of deformation of this structure and look for non-trivial deformations. From time to time, they are only equivalent. You can deform something, but you will get something which is equivalent. But of course, the non-trivial facts are, non-trivial things exist when you have non-trivial deformation. So the same structure have different non-inequivalent realizations. Exactly this is the relation between quantum mechanics and classical mechanics. They are two inequivalent realization of the same structure of algebra of observables, and the parameter which connects somehow, which is parameter of deformation, is nothing but Planck constant, a dimensional constant which was introduced into physics in the beginning of the century by Planck and Einstein and others, which somehow manifested itself, the distinction between quantum mechanics and classical mechanics. In the theory of deformations, there is one more important notion, namely stable deformation. The structure is called stable if every realization of the same structure which lies in the vicinity of given structure is equivalent to it. So if you cannot infinitesimally deform your structure into an equivalent one, you say that your structure is stable. And as my friends Professors Lichnerovitz, Flatot, and Steinheimer have shown, the classical mechanics is unstable. Its deformation to quantum mechanics is non-trivial one, and Planck constant can be taken as formally as small as you want. On the other hand, quantum mechanics by itself is stable. So you cannot think that if your structure are fixed, then you will find a theory which is nearby but inequivalent to quantum mechanics. So one of the, so I can say in alternative way, one of the main revolution in theoretical physics of the century, namely passage from classical mechanics to quantum mechanics, was nothing but deformation to a stable structure. I'm afraid that I maybe sound a little bit conservative. I don't say that it was revolution, it was just deformation, and moreover, it was deformation to a stable structure. But nevertheless, this is a fact of life. Physics is quite conservative, I would say. So what we remember, what we have got until now. First, there are structure in the, one can axiomatize physics in such a way that you have some particular structures. The history of physics have shown that we have deformed this structure, come to a stable one, and the parameter of deformation, the Planck constant, h it's denoted usually, is a dimensional parameter. We have special dimension of action. Well, I will not tell you, but we know that there are just 3 dimensions in physics: length, time, duration, and mass. So a particular combination of these 3 dimensions is dimension of action, and Planck constant is dimensional one. Now, what can we say about another revolution in theoretical physics of this century, namely about passage from relativity? This is Lorentz group. The formulas of Lorentz transformations are deformation of formulas of Galilean transformation. And a parameter which enters these formulas is nothing but velocity of light, c. And it is equal to infinity in classical case, in the case of non-relativism. So it's rather 1 over c, which is a parameter of deformation. 1 over c is 0 for classical case, and non-zero for relativity. Once more, it turns out that Galilean group was unstable. Lorentz group is stable. It's semi-simple and it's stable. So the second revolution was also nothing but deformation into a stable structure. And that's a fact of history now. Given these things, one cannot help speculating about if there will be more deformations in the development of theoretical physics. The phenomenological fact was that the 2 deformations which until now occurred were connected with dimensional parameters, velocity of light and Planck constant. And as I told you, there exist only 3 independent dimensions in physics. It's not dimensions of space, it's just 3, as I told you, duration of time, length, and mass. So the simplest speculation would be to say, all right, we are to have one more deformation, but we have to find of what structure, which will be associated also with dimensional parameters. Usually, physicists think that the new dimensional parameter, which must be introduced into future theory, have dimension of length. So that's why people used to say about search for fundamental length. So what are possible candidates for such a deformation? One of them could be formulated still in terms of special relativity. Indeed, I have mentioned you about the part of Galilean group, or that one which did not mention the translations in space-time. So 6-dimensional group can be extended to 10-dimensional group if you add these translations in space-time. And of course, the same translations come into relativity, and so we speak about Poincaré group, which contains Lorentz group and translations, 10-parameter group. This group is unstable, and so it can be deformed. And of course, it's known that it can be deformed, and the deformed group, which is stable, is called de Sitter group. So one of the possibilities, and of course there is a dimensional constant associated with this deformation, which is radius of de Sitter universe. And so one of the possibilities would be to think that just going to de Sitter universe from Minkowski universe will give us the third deformation. But to my mind, this is a little bit, well, we know now that not all phenomenology can be embedded in this too restricted form, and so we have to look for something else. Well, another possibility is to say that we already have such a deformation, and this is gravity theory, theory of gravity of Einstein. Indeed, in gravity, what we do, we substitute Minkowski space, which is flat, by general Riemann or pseudo-Riemann space, and certainly we can say that generic non-linear space is stable, whereas linear space is unstable in some evident sense. Then the parameter of deformation which comes into formulation of Einstein theory of gravity is Newton constant of gravity. And it gives you the third dimension, and so on. So with these things in mind, one can say that deformation, well, unification of quantum mechanics, relativity, and gravity could be an ultimate physical theory. When it will be achieved, then physics as fundamental science will be finished. This, I understand that what I say is a little bit too much, maybe, and all these pure speculative mathematical schemes from time to time fail in the history of science, but nevertheless, it's quite attractive to me, and as a mathematical physicist, I can allow myself to speak about it. I don't think that, in fact, the prediction that fundamental physics will be finished is too strong. In fact, such science as chemistry, from fundamental point of view, is finished, because we now know that it's nothing but theory of Coulomb systems and so on. Of course, it doesn't mean that chemistry is finished as a science. It's just the opposite. But fundamental aspects of this are known. I hope that the same could happen with two physics. But, of course, small, minor difficulty remains, namely that we still don't know how to unite gravity, relativism, and quantum mechanics. In spite that Moshe told you that I have formulated several things for quantum gravity, these things are too formal and could not be considered as a final solution of finding quantum gravity or universal physical theory. In recent years, we had another speculation around this, which can be somehow still covered with these general principles, namely the construction of another approach to gravity through so-called strings and superstrings. There also, of course, we have dimensional parameter, which is called string tension, and this theory is another possible candidate for unification or for universal deformation of three structures which must exist in physics. So maybe I'll stop my speculations here. I wanted to tell you that looking back into history, formulating it in modern way, give you some give you some foresight into future. And this interrelation, and of course all these facts which are connected with natural science, with physics, are written or expressed in terms of pure mathematical language. So that's, in this way, I return to what I begin with. Mathematics plays very inherent role in the formulation of physics, it is its language, and one cannot understand physics not knowing this language. Thank you.
Thank you very much, Ludwig. On remercie L.D. Faddeev pour cet exposé très brillant. Et je crois que la règle de jeu, c'est qu'il n'y a pas de questions ou il y a de questions. Est-ce qu'il y a des remarques ou des questions? Bref, on accepte. Bon, alors merci beaucoup Ludwig. Et